The symphony of weights and inputs, a mathematical journey into neural networks. Welcome, fellow data enthusiasts, to a dive into the mathematical foundations of neural networks. Today, we'll unveil the intricate dance of weights and inputs, the hidden language that allows these networks to learn and perform extraordinary feats. Buckle up, for we're about to embark on a symphony of summation and equations. Act 1. The neuron's playground, weighted sums and activation. Imagine a single neuron, a processing unit at the heart of the network. It receives a set of inputs, each representing a piece of information, like pixel values in an image or features in a dataset. These inputs are multiplied by weights, numerical coefficients that act as connection strengths. This weighted dance is orchestrated by a summation, where all the weighted inputs are combined. Weighted sum equals sigma w underscore I asterisk x underscore I. Here, w underscore I represents the weight assigned to the ith input, and x underscore I is the value of the ith input. This sum captures the overall activation of the neuron, a measure of how excited it is to fire. But the story doesn't end there. This weighted sum doesn't directly tell us the neuron's output. There's one more crucial actor, the activation function. This nonlinear function transforms the sum into a meaningful output, often between 0 and 1. Think of it as a filter that decides how strongly the neuron should respond to the combined input signals. Act 2. The orchestral layers, building a network of neurons. Neurons don't work in isolation. They form intricate layers, stacking up like instruments in a complex orchestra. Each layer receives outputs from the previous layer as its inputs, feeding information forward through the network. Imagine the weighted sums and activations rippling through the layers, transforming simple inputs into complex outputs like predictions or classifications. Act 3. The learning waltz, gradient descent and weight updates. But how do these networks learn? Imagine we present the network with an input and compare its output to the desired target. The mismatch between these values is called the error. Our goal is to minimize this error by adjusting the weights in a way that brings the output closer to the target. This is where the graceful steps of gradient descent come in. This optimization algorithm calculates the gradients, the directions and magnitudes in which we should nudge the weights to minimize the error. It's like a conductor carefully adjusting the instrument's weights to achieve perfect harmony, reduced error. With each training iteration, the weights are updated based on these gradients, guiding the network towards better performance. Finale, the mathematical score, equations and notation. So far, we've painted a conceptual picture, but the true language of this symphony is mathematics. Here's a glimpse into the equations that govern the dance of weights and inputs. Weighted sum equation, sigma w underscore I x underscore I plus b, where b is the bias term, a constant offset adding flexibility to the neuron's activation. Activation function, various functions like sigmoid, than, or relu are used to transform the weighted sum into an output. Gradient descent equations, complex formulas calculate the gradients of the error with respect to each weight, guiding their update. Encore, beyond the basics. This lecture merely scratches the surface of the mathematical symphony of neural networks. We haven't delved into backpropagation, complex network architectures, or optimization algorithms.